Now, young slits are easy to understand if we think of light as waves, for example. If, however, we think of light in terms of these photons, the particles, we start to have more conceptual difficulty. Similarly, if instead of thinking about light waves incident in two slits, we think about an electron wave incident on those same two slits, we have some apparent problems. Now, we should understand we can actually do this kind of experiment with electrons, so we can see what happens. And we can arrange to have an approximately monochromatic electron beam, as I said before, by carefully pulling electrons out of a metal in a vacuum with a voltage. And we can effectively make them incident on those two slits in a good enough approximation to a plane wave. The typical conceptual problem we now have is that our classical intuition tells us that a particle has to go through one slit or the other. Surely a particle cannot go through two slits. But if we insist the particle goes through one particular slit, we actually get no interference pattern.
So let's look exactly at that. If we block our upper slit here, there is no interference pattern. We just get a kind of uniform, not very bright pattern over here, as shown by this dark green bar. Similarly, if we block the lower slit, there's no interference pattern. So if we insist that we know for sure which slit the electron went through by blocking it, we don't get any interference pattern.
We might try to resolve our difficulty by saying that somehow the interference pattern results from the interference of some particles going through the upper slit and some going through the lower slit. However, and here is possibly a major surprise, if we set this experiment up either with light or with electrons, so that we are fairly sure there is only one photon or one electron in the apparatus at a time, which we can always do just by turning down the light beam or the electron current, we still end up by building up the interference pattern. And in this case, what happens is that for each electron or photon in the apparatus, we get a dot on the screen. And if we keep repeating this experiment and allow this pattern of dots to build up on the screen, it will build up into the interference pattern. Part of our difficulty here is that our classical intuition insists that particles should have definite position. That's lurking in the back of our brains here, that we think that must be the case. They have to be somewhere specific. In fact, with quantum mechanical particles like electrons or photons, we simply do not require that this is the case. Our classical view tends to make us think of the electron or the photon as being some small object of a definite size that has to be somewhere. As far as quantum mechanics is concerned, there is actually no specific size for either the electron or the photon. They can be in states that have characteristic sizes, which here is essentially the characteristic size of our waves on the diffraction pattern. Note that in this case, the size of our particles is therefore larger than the separation between the slits. Now, we should note, of course, that when the electron or the photon hits the screen, it makes some definite mark at a specific position. The quantum mechanical view of this is that the act of hitting the screen causes a measurement of position to be made. And we say then that the wave function collapses into one with a definite position, with a probability given by Born's rule. That is, the probability that the electron is found at a given position on the screen is proportional to the modulus squared of the wave function at that point. It's important to emphasize that we are not explaining this measurement process or this wave function collapse. Indeed, it is quite debatable that we do not know how to do that. Nonetheless, if we take this rule as a pragmatic one for the purposes of statistical calculation, we get the behavior we predict. This kind of way of describing such an experiment is one that typically causes great consternation and perplexity the first time we come across it. What we can say is that if we follow our calculation of the behavior of this wave diffraction and we use Born's rule at the end, we get results that agree with the experiment. However, we may well have to abandon our idea that the electron has a definite position before we measure it. The question of which slit the electron goes through can be regarded as meaningless. If we establish which slit it goes through, such as by blocking one slit or the other, we lose the interference pattern. We can either have the interference pattern, or we can know which slit the electron went through. We cannot have both. If, however, we merely ask to calculate things we can measure, such as the probability that we'll find the electron landing at some particular position on the screen, quantum mechanics calculates that perfectly well. What was it you wanted to measure?